Hello and welcome to episode 6 in this series on differential geometry. In this episode, we talk about differential forms. A differential form, phi, is an expression obtained by adding and wedge multiplying real-valued functions and the differentials dxi. When each term in the sum contains p dxi's, that form is called a p-form. In particular, if each term in the sum has only one dxi, so for example, something of the form f dx plus g dy plus h dz, we would call that a one form, and that's the subject of the previous episode. Note, the rules for addition and multiplication for these differentials are associative and distributive each. But we have a new law, the alternation rule, which governs the multiplication of these differentials. The product dxi, dxj, which is in fact a wedge product, as we call it, is the same as the product dxj, dxi, except now there's a minus sign. We prove the following lemma. If phi and psi are one forms, then phi wedged with psi is equal to the negative of psi wedged with phi. So this is a more general alternation rule for differential forms. We apply the alternation rule on all of the terms of the wedge product in order to obtain this lemma. Writing phi as a sum of the dxi's with function coefficients, you might say, called fi, and psi being the same, except we'll call those function coefficients gi, we obtain the wedge product by simply computing the product of all of the terms of the first times all the terms of the second. This gives us a sum over two indices, say. Then we can simply use the alternation rule on each term to obtain the second equality. And the third equality is from the definition the same way we got the first. So that proof is quite straightforward. Next, we define the exterior derivative. Given a one form on R3, the exterior derivative of that form is written d phi, where we simply compute the wedge products on each of the terms in the following way. If the ith term is fi dxi, then the exterior derivative of that term is dfi wedged with dxi. Next, we have a theorem. The theorem gives us linearity statements about external derivatives. Specifically, the theorem states, given functions f and g and one forms phi and psi, then the exterior derivative of the zero form fg obeys the product rule that we proved in a previous section. The exterior derivative of the one form f phi obeys this sort of new product rule, which is written under the second bullet. And thirdly, the exterior derivative of a wedge product gives this product rule, which has a negative sign. The first statement is a previous theorem, so we don't need to prove that. The second statement is actually a particular instance of the third. If we allow f to be a 1 form instead of being a 0 form, then f phi would be just a wedge product of the same kind that phi wedged with psi is. So we'll treat that as assumed given the third statement. So we prove the third statement. Consider, for conciseness, phi equal to f dx and psi equal to g dy. The general statement follows by repeating all such combinations of the differentials dxi. On the left-hand side, we have the exterior derivative of this wedge product being, by definition, the exterior derivative of f g dx dy. Definition, the exterior derivative of fg dx dy is the derivative of fg times dz dx dy. Using our familiar product rule from Calculus 3, we can simply write this expression as f times the partial derivative of g with respect to z plus g times the partial derivative of f with respect to z dx dy dz. On the right-hand side of statement 3, we have this difference of wedge products using the definition of phi and psi. We substitute in to these wedge products. Then we use the definition of the exterior derivative on these 1 forms that we've substituted in. And then we use the alternation rule on the second term to get a second negative sign, which of course cancels out. Then we have 2 positive terms, and their sum is exactly the same as what we obtained for the left-hand side. Thus, we prove Theorem 6.4, and we have all of these product rule-like statements at our disposal for future use of differential forms.